Welcome back to Math 104. The least possible probability an event could have is 0, precisely because the relative frequency cannot be less than 0. This fraction cannot be less than 0. Similarly, the greatest possible probability of an event is 1, since this fraction cannot be greater than 1. So it's not just by declaration that probability is a number that ranges from 0 to 1. It's because of this definition. It's a consequence of this definition of probability as long-term relative frequency. And relative frequency is a fraction between 0 and 1. Between those two extremes of 0 and 1, any real number can occur. How does the probability of an event relate to the probability of the outcomes in it? This is mercifully straightforward. The probability of an event just equals the sum of the probabilities of the outcomes in it. And this makes conceptual sense. Again, this is not just a declaration. Instead, this is something that we could reason out. Let's look at an example. In our example, a Rutgers student is selected at random and asked, "What is your class year?" By class year, I mean freshman, sophomore, junior, senior. So those are the outcomes. Those are the most basic answers that the randomly selected student could give. And let us suppose that these are the associated probabilities of these outcomes. These aren't exact numbers, but they are a reasonable conjecture. A student is selected at random. We can ask, what is the probability that this student is a sophomore or junior or senior? That is the event. To be a sophomore or junior or senior. Now when you perform this experiment, 24% of the time, the person you're surveying is going to be a sophomore. A separate 23% of the time, the person is going to be a junior. And a separate 26% of the time, besides the other two percentages, a separate distinct 26% of the time, the person is going to be a senior. So it makes sense that the overall percentage of the time that you're getting a sophomore or a junior or a senior is the sum of the probabilities of the associated outcomes. And that turns out to be 0.73. There's a 73% chance that the person you're surveying is a sophomore or a junior or a senior. Notice that in this example, the outcomes are not equally likely. The outcomes do not all have the same probability as one another. In some experiments, the outcomes are equally likely. And these turn out to be a very important category of experiments. For example, flipping a fair coin, heads is one outcome, tails is another, and by the fairness of the coin they are equally likely. Similarly, rolling a fair die. The possible outcomes are 1, 2, 3, 4, 5, or 6. That is the number on the die that appears face up when the die lands. And if the die is fair, that means, again, theoretical probability, that means that these outcomes are equally likely. When we work with an experiment where the outcomes are equally likely, probabilities are easier to think about. For example, when we roll our fair six-sided die, since there are 6 outcomes, each has probability 1/6. We can ask now about a more interesting event. We can ask, what is the probability that when you roll, the number will be odd? There are 3 outcomes in this event, namely 1, 3, and 5. Each one of these outcomes contributing to that event occurs 1/6 of the time. Let's denote this event E and say that the probability of E equals 1/6 from the 1s, 1/6 from the 3s, plus 1/6 from the 5s. Each one contributes 1/6 to the overall fraction of the time that this event occurs. And that comes out to 3/6, which if you really insist, you can simplify to 1/2, which is 0.5. For purposes of this course, it will often be better, actually. It will often be clearer to leave fractions unsimplified. The bottom line is that finding the probability of this event was ultimately a matter of counting how many outcomes are in it, and dividing that total, 3, by the total number of possible outcomes, namely 6. And that's exactly how we're going to think about these kinds of experiments in general. So in general, when we are performing an experiment with equally likely outcomes, the probability of an event, E, equals the number of outcomes in that event, E, divided by the number of outcomes in the sample space. In other words, we can describe this as the number of ways E can occur, that's another way of saying the number of outcomes in E, divided by the total number of possible outcomes for the experiment. As a result, a certain amount of our work in this subject will be a matter of counting numbers of outcomes, whether in an event or in the experiment as a whole. You will often be told in the wording of a problem that the outcomes are equally likely, but this assumption might be hidden in the wording. For example, if it says that you are flipping a fair coin, you must recognize that this means that the outcomes are equally likely. This is something to watch for. Recall our favorite experiment of observing the birth order in a randomly selected family of 3 children. We've already seen a couple of times the sample space, the complete list of all possible outcomes, and we're going to assume for now that these outcomes are equally likely. This is not exactly true in real life. In real life, boys are slightly more likely at each birth than girls, but for now we're going to pretend that they really are equally likely, and we can ask, what is the probability of the event that there is exactly 1 girl and exactly 2 boys? Not necessarily in that order, in any order. We have BBG, BGB, or GBB. Each of these contributes to our outcome. We've already seen this since the experiment has 8 equally likely outcomes, each with probability 1/8. Each one of these is occurring 1/8 of the time in the long run. If we survey many families with 3 children and ask each one for the birth order, roughly speaking, it'll turn out that 1/8 of them have 3 boys, 1/8 of them have boy, boy, girl, etc. That means that the probability of this event equals 3/8. There are 3 outcomes in it out of 8 outcomes total. Again, this thinking only works because the outcomes are equally likely. Another example. What is the probability of the event there is at least 1 girl? Well, there are 2 ways to think about this. The hard way is to list all the outcomes that count towards this event. Wait, I thought that's what we're supposed to do. Well, that's certainly what you always can do. Here we can go and list them all: boy, boy, girl, boy, girl, boy, girl, boy, 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 girl, 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 boy, girl, 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 boy, and girl, girl, girl. Each of these outcomes has at least 1 girl, and these are all the outcomes that have at least 1 girl. And we can count up 1, 2, 3, 4, 5, 6, 7. If we denote this event F, then we conclude that the probability of F equals 7/8. And that is a perfectly fine way to solve this problem. But there is an easier way. The easier way is to note that the probability of the full sample space, the probability that something happens, is 8 out of 8. Each of the 8 outcomes in the sample space contributes 1/8 to the probability that something happens. Right? The probability that something happens equals 1. If the probability of the event with all 8 outcomes in it equals 1, then the probability of this event F here, which consists of all the outcomes except for 1, it's missing the 1 outcome BBB, the probability of our event F here should therefore be 1 minus 1/8. It's the probability of the full sample space minus the fraction of the time that all boys occurs. Another way of saying it is that our event F has only a 1/8 chance of not occurring, therefore it has a 7/8 chance of occurring. 1/8 of the time F doesn't occur, the other 7/8 of the time F does occur. 1/8 of the time there are all boys, the remaining 7/8 of the time it's not the case that there are all boys. There is something other than all boys. We'll say more in later videos about the principle at work here. Before going on to the next video, answer the following question about our experiment of randomly selecting a family with 3 children and asking about the birth order. What is the probability of the event there is at least one girl and at least one boy?